ఒక చాక్ పీస్ సరిపోతుందా? చాలా ఎక్కువ. Okay. Morning to you all. I am Ravi Kumar Reddy, Assistant Professor in the Civil Engineering Department. Let us have a brief discussion on deflections of beams. Beam deflections are necessary after the limit state method has come into picture. The design methods of beams, the three methods of beam designs are structural element designs like ultimate load method, working stress method. The latest is a limit state method. Limit state method requires that any structural member should be safe as well as serviceable. That serviceability conditions have been incorporated in this method. It is adopted in the latest IS code. Hence, deflection calculations are must to design any structural member using this limit state method. Working stress method was the method which ensures the safety of a member, whereas limit state method ensures both safety as well as serviceability. Service in the sense, say if in a room, if a beam deflects excessively, we cannot sit in that room. A psychological feeling that the beam is going to fail, it won't fail, whereas excessive deflection makes you to feel that it is going to fail. That is psychological failure of a beam. Okay. So, to avoid that, we need to calculate the deflections of structural elements like slab, beams. Not only that psychological feeling, the flooring will be damaged. If the slab, some of the buildings, when you walk on the floor, you feel different sound when you touch any tile. When you put a feet on the tile, we feel a different sound, meaning that it has lost its contact with the slab or floor, meaning that the slab deflected. So, the tiles cannot deflect. The amount of slab deflection, it cannot cooperate with the tiles deflection. So, the tiles are flat. Once this top length gets reduced, the tiles has to come closer. That facility you did not provide. So, tiles will be broken. Sometimes removal of joint between the tile and the roof. So, that is a problem with the excessive deflections in structural elements like slabs and beams. Okay. So, this is the background information why the deflection calculations are required. Deflections are calculations are must to see that a beam should service throughout its lifespan designed and to not to cause any damage to non-structural elements like flooring, tiles, cover provided for the slab. Sometimes you will be looking at cover removed from the slab, you can see the reinforcement. That problem is because of excessive displacement. Cracking of tiles occurs at top, cracking of cover occurs at bottom and falls down, removal from the slab, and you can see the reinforcement. Once reinforcement exposed to the environment, environmental attack happens, rusting, all that takes place. Steel will no longer service its job. So, failure of reinforcement is a failure of element itself. Because of all these reasons, we want the deflections of beams to be calculated. Okay. There are different methods to calculate beam deflections. The first method is direct integration method. Second one, area moment theorem, area moment method you can say. Third one, conjugate beam method. There are three methods to calculate deflections of beams. Direct integration method is in fact developed by Bernoulli, Jean Bernoulli. You may be knowing this name, famous name. Scientist Bernoulli developed this method and further extensively used by Euler. This method, after the development by Bernoulli, it is extensively used for even columns to the Euler. Euler applied this concept to columns also. Area moment method is a geometrical one, simplified method, geometrical method. That is developed by Moore, scientist Moore. Okay. Conjugate beam method is a special case of area moment method. Each method is having its own advantages and disadvantages. We will go on discuss each one. First, coming to direct integration method. It involves integration of some equation to get deflections of beams. Okay. We need an equation which represents the deflected shape of a beam. Generally, a beam is an element where lateral loads prevail on the beam, provided with some type of support, commonly simply supported, cantilevers or overhanging. Right. If any beam is loaded with lateral loads, it will bend. The amount of deflection delta or y, if you have an equation for this curve, I can calculate the value of deflection anywhere I want. Say for example, if you say this is x coordinate, y coordinate of the curve, points on the curve will be represented by x, y coordinates. X denotes location where we want deflection, y denotes the value of deflection in a beam. Okay. So, if we can have an equation for this, I can find the y value wherever the deflection is required. Okay. The development of equation for this deformed shape is done by two steps. One, first relating strain of a fiber chosen layer in a beam, relating strain with the curvature of the beam. Strain and curvature relation first we must establish. Next step, moment curvature relationship must be established. Two steps required to develop an equation for the deformed shape of a beam under loading. Okay. These two steps are in fact from simple bending theory or pure bending theory. It is already discussed in the semester 1. Okay. Simple bending theory gives you these two relations. I will straight away give these relations. Strain curvature relationship, strain in any layer of a beam is equal to y by rho. Y, location where fiber is selected, layer is selected. Rho, radius of curvature of the bent shape or curve. Okay. We know that when you load the beam bent in the form of a curve, geometry of the curve, geometrical property is a radius of curvature and curvature. 1 by rho is curvature, rho is radius of curvature. Okay. So, this is a strain curvature relationship. Excuse me. Voice రావట్లేదు. ఏమైందండి? మేబీ అంటే షర్ట్ మూవింగ్ దానివల్ల. ఓపెన్ చేద్దాం సార్, ఇటువైపు పెడితే. Okay. So, to find deflections of beams using direct integration method, we want an equation which represents the bent shape of the beam, that is developed in two steps by strain curvature relationship, strain in a layer, curvature of the bent shape, then moment curvature relationship. Moment curvature relationship is by simple bending equation. The simple bending equation from the first semester m by I, sigma by y, e by rho. From this we have ready-made moment curvature relationship, moment curvature relationship, strain curvature relationship. Combining these two, we can develop an equation for curvature of this curve. Okay. How we do that? This is the strain from geometry. Equate that strain from geometry to the strain from theory. Strain from geometry is this, strain from theory we equate it. How it is? Like say m by I, sigma by y, where sigma is equal to my by I. Strain from Hooke's law, stress by Young's modulus, strain from theory, where sigma is equal to my by I, my by ei. This is the strain at any layer in a beam from theory, strain from geometry, equating both, that is my by ei is equal to y by rho. Y gets cancelled. 1 by rho is m by ei. 1 by rho is curvature of this bent shape, curvature. From the analytical geometry, curvature of any curve can be written in Cartesian coordinates, d square y by dx square 1 plus dy by dx whole square whole power 3 by 2. This is the curvature of a curve from the analytical geometry in Cartesian system, where denominator consists of a slope dy by dx. Okay. For practical cases of beam deflections, generally beam length of the beam of the order of 3 meters to 5 meters. So 3000 mm, say for example, in a case of 3000 mm length of beam deflecting by a nominal amount of 20 mm roughly, so the slope of this bent shape, slope value 1520 mm, so tan theta is 20 by 1500 is a very less number. So slope is negligible in case of beams bending as a curve. So if you neglect this slope, the curvature become d square y by dx square. Neglecting this value, this is a negligible one, put it 0, 1 power 3 by 2, denominator become 1, numerator d square y by dx square remains same. So 1 by, in place of 1 by rho, we replace d square y by dx square. So this is the expression which help you to find deflection. What is y is nothing but this has come from curvature. X comma y are the coordinates of points on the curve. Y denotes vertical coordinate of a point on the curve, that is nothing but deflection. So d square y by dx square is m by ei, bending moment at any section relating deflection. Okay. So this equation relates bending moment with the deflection. We have a question that beams, internal forces generated in a beam are 3: axial, shear, bending. Having defined the beam which is loaded with lateral loads, axial loads are absent. So axial reaction absent. No axial forces develop in a beam. Coming to the other two, bending moment, shear force. Shear force is there, but what we are doing here, considering only bending moment, shear deformations are also there, they are neglected. Okay. There are theories developed for finding shear deformations also, but they say that compared to deformations created by bending moment, shear deformations are very very less, you can neglect them. Okay. So, in total, because of lateral loading on beam, the deflections can be conveniently calculated without much error with this formula. Okay. So, the final formula what I can give you to calculate deformations by integration technique, direct integration technique, d square y by dx square. This is the equation which relates bending moment to deflection. If we want y value, we need to integrate this equation twice. So, that is why the name related to integration technique name is given based on the idea that we have to integrate the equation of the elastic curve, that is the bent shape of the beam, so that we will get the deflection value. Okay. So, in integration process, we need to integrate twice to extract y from this. So, integration should be done twice. There will be two integration constants, namely C1 and C2. To evaluate C1 and C2, we must use some known conditions, the boundary conditions, such as depending on the types of supports provided to a beam. Say for example, if you have a cantilever beam fixed at one end, free at the other end, boundary conditions, that means known conditions to solve integration constants are at fixed end slope 0, dy by dx 0, deflection 0. Using these two known conditions, those are boundary conditions, you can estimate y from this equation. Okay. This is the direct integration technique which helps you to find deflections in a beam. Let us see an example how this method is used. Simple example to estimate deflection at any location where you want using this method. Take a cantilever of length L which is applied by a concentrated force P at free end. Notate the beam AB. I am interested in slope at B, deflection at B. To calculate slope and deflection, we know that the beam has got some cross section, so it will have some I value. Beam will be made of some material, maybe steel or concrete. It will have Young's modulus. Okay. So, coming to applying this equation to that beam to calculate deflection, let us consider a section where we want to write moment equation. So, consider a section x at a distance of x from A or from B, from either end. Okay. Separating that portion x, force P x. Why the right part is considered is to avoid support reaction calculation to the left. Moment at a section, from the first semester discussion, moment at a section is equal to sum of all moments to the left or to the right of a section. So, I am considering here right of the section. Sum of all moments to the right side of this section, mx, moment at x force P into x. Considering sign convention, moment causing hogging will be negative, moment causing sagging will be positive. This force into distance causes a moment like this, which will push the beam up, meaning that it creates concavity downward, is called hogging. Concavity downward is called hogging. So, it creates hogging moment, hence we put a negative sign, moment is negative. Okay. This is the moment at any location in this beam. This represents, moment equation represent moment at any section, at any location. If you go on place x values, it will give you bending moment values at different sections. If x is equal to 0, bending moment at B is equal to 0. X is equal to L, bending moment at fixed support is P into L. So, moment can be calculated at any point from A to B. Applying this in deflection equation, EI d square y by dx square is equal to minus Px. This is the substitution for moment. If you go on integrate this, say dy by dx, integrating minus P x square by 2 1 by EI comes into picture plus C1 integration constant. Again integrating that 1 by EI x cube by 6 C1x C2. These are the two equations which represent slope at any point in the beam, deflection at any point in the beam. I told you that to evaluate the C1 and C2 integration constants, you can use known conditions that slope is 0. If you can draw the bent form of this beam, this is likely to bend like this. So, the slope at this point is 0, deflection is 0. I am interested in what is the slope value, this is theta b, what is the deflection value yb. Those two values will be found from these two by evaluating integration constants C1 and C2. Say for example, by substituting dy by dx is equal to 0 at the fixed end means x measured from B. So, fixed end x value is L, substituting x is equal to L here, dy by dx 0 at x is equal to L, dy by dx is equal to 0 is the boundary condition. Substituting here we get C1 value 0 is equal to PL square by 2 EI plus C1. So, C1 value is equal to PL square by 2 EI. Similarly, substituting the other boundary condition x is equal to L, y is equal to 0, we can estimate C2. Those two equations after solving C1, C2 can be readily used to find anywhere in the beam slope and deflection values. This is the way we apply this method. Further, this method has got advantages and disadvantages. To overcome them, it is modified or given some simplicities in terms of singularity functions. That means advantages that you can plot deflected shape of a beam. Why? Because we can estimate slope and deflection values at any location with a single equation. So, you can plot the deflected form of the beam with a known equation. At any location of the beam, we can estimate deflection at any point which you are interested in. Advantages, disadvantages. It involves cumbersome procedure as you need to integrate. If it is a simple beam and simple loading, the equations are simple. If we go for a complex loading, equations become bigger, integration become tedious. So, the disadvantage with this is integration process is going to be much difficult when you go for higher level of loading, and the variation in beam cross sections, all that difficulty levels if you introduce. Okay. So, these are the advantages and disadvantages with this method. To reduce the complexity in case of load discontinuity, flexural rigidity discontinuity, all that, there is a simplification given to this direct integration technique, what is called the introduction to introducing singularity function will reduce the complexity of the problem. How it is, right? So, for example, there is a cantilever beam that if I have two loads P1 and P2, from A to C, to represent the deflected form of beam from A to C, I need a moment equation. Upon substituting into the equation for deflection integration, I can calculate deflections from A to C only. The moment equation which is written for portion A to C is not applicable from B to C. So, we need one more equation, moment equation, which represents this region. So, as number of discontinuities increase in loading, number of equations go on increase. So, it becomes a very lengthy process and the integration involves much difficult. Hence, Macaulay introduced a method by introducing some functions which will help you to write a single moment equation which can be used throughout the beam. Say for example, for this beam itself, if you formulate Macaulay's moment equation mx, direct integration technique, we want to separate the beam into number of portions where the load condition is uniform, and we must integrate to evaluate deflections. Whereas in case of Macaulay's technique, a single equation is sufficient. Macaulay suggests that you choose a section at either end of the beam. We choose this end of the beam, measure that section from the opposite end of the beam, this one. Locate the section from the opposite end, then write the moment equation. Say I want moments at this section, consider the portion of the opposite end. So, moment because of P1 is equal to P1 into x minus, say for example, this is L by 2, L by 2, x minus L by 2, P1 x minus L by 2 is the moment caused by P1 at section XX, which will be again a negative value, creates hogging. Again P2 into x minus P2 into x, moment because of P2 at this section, force multiplied by perpendicular distance is x. So P2 into x. This is the moment equation which is valid from A to B. No need of two moment equations, separate moment equations. Okay. So this equation, when you substitute in the equation for deflections, minus P1 x minus L by 2 minus P2 x, Macaulay suggested that the multiplying parameter for force whatever is introduced must be retained as it is throughout the integration. Do not alter this function, meaning if I integrate this once, become dy by dx left hand side, right hand side integration minus P1, integrate it as a single function. Do not integrate this like x square by 2 minus L by 2 x. It should be integrated like x minus 2 L by 2 whole square by 2. It should not be integrated like x square by 2 minus L by 2 into x. Retain the function as it is. Similarly, P2 x square by 2. Further integration should be carried out, which gives you, say for example, y ei into y is equal to further integration minus P1 by 2. Integration of this function square will be function cube by 3, x minus L by 2 cube by 3. Okay, it should not be integrated by expanding this a minus b whole square, should not be integrated. The function should be retained as it is, minus P2 by 2 x cube by 3. The integration constant as usual plus C1x plus C2. Okay, so this is the way we go on. The further procedure is similar, like substituting for boundary condition, evaluating C1 and C2, we can formulate a single equation which will give you deflection value for any discontinuity in loading. Whatever may be the loading discontinuity, it will accommodate everything in this moment equation which is suggested to write. The points to be noted is, from the Macaulay's technique, it is to be used whenever you observe any discontinuities in loading, discontinuities in EI value, that means flexural rigidity of the cross sections. Okay. So to write that, the steps to be remembered, Macaulay's technique to be used is, first thing, choose a section at end of a beam, either end of a beam, measure that section from the opposite end, measure that section from opposite end, write a moment equation with the function, retain the function as it is throughout the integration. Some more points to be noted when you use Macaulay's technique is, when there is loads like moments UDLs, when you have an applied moment M on a beam, how to write Macaulay's technique moment equation. we take a section xx measured from the opposite end, mx is equal to moment at that section, sum of all moments to the right, it is just m, it is negative. So, minus m is the value, moment equation. Whereas, if I go on integrate this ei d square y by dx square minus mx plus c1 dy by dx ei into y minus mx square by 2 plus c1x plus c2. Okay. If I go on integrate like this, the function what is here which represents the distance parameter of the moment is missing, okay. Whereas it is present here, a force multiplied by a distance function, where it is missing, that function is missing. If you carry out this by direct integration technique, there is no problem, you can carry on. Whereas to use Macaulay's technique, we must introduce a function, singularity function. What it denote here is m, it is at a distance of x power 0 I introduce, m into 1 without any change of value. We do not disturb the value, but we introduce a function. So, here x power 0, now come x power 1, x square, like that. So, the function is retained as it is in the integration. Okay. So, such care must be taken when there are applied moments. So, applied moment should have a singularity function power 0, concentrated force should have concentrated forces should have singularity function power 1. Similarly, UDLs, if we have uniformly distributed load applied on a beam, to write Macaulay's technique, why? Because he see here there is no load here, loading condition is uniform from A to C. At C, loading condition is changing, there is discontinuity here, there is discontinuity here, two discontinuities. So, uniformity portions are 3. A moment equation is required in this region, moment equation is required in this region, another moment equation is required in that region. So, 3 moment equations. If we use direct integration technique, we need to formulate the 6 equations, 3 slope equations, 3 deflection equations, 6 into 2, 12 constants, integration constants. This much tedious this is when you use direct integration technique. So, if we go for Macaulay's technique, by choosing a section at either end, maybe in this region or maybe in this region, to avoid support reaction calculations, I choose this section. So, if I write mx value, this is W, say L by 3, L by 3, L by 3, 3 regions having equal length, let us say. If I want to write moment of this one, W into L by 3 equivalent concentrated load multiplied by distance x measured from this end, x minus up to this, the distance what you have to write is this one. So, remaining distance is x minus L by 3 plus L by 6. we must deduct this distance. Equivalent concentrated load will be at center of the UDL. So, x minus L by 3 plus L by 6. Okay. Now, if you see the function which is the multiplier of the load having power 1, which is nothing but concentrated load. This moment equation is not representing UDL, it is representing concentrated load. So, there is a error committed. The UDL is not represented here, it is representing concentrated load, but actually the beam is having UDL. How to represent it? If such cases arises, you need to extend the UDL into the portion through the section till the other end. Deduct the same. Now, moment equation changes. This is a wrong representation of moment equation. The correct representation is by, this is now W extending from here to here, A to D. So, moment because of that is W into x minus L by 3 into x minus L by 3 by 2, which is again negative. There is UDL here also, deducted one to balance this added one. This is added additionally to facilitate Macaulay's technique. This is deducted one to not to change the given condition. So, plus now, why? Because this is the beam, this is the section taken, this is the load I have. It is nothing but an upward load which creates a moment sagging. So, positive nature. Okay. W into x minus the distance up to this is 2L by 3. 2L by 3 is the equivalent load value. Distance from this load to the section x minus 2L by 3 by 2. So, now see the function minus W x minus L by 3 square by 2 plus W into x minus 2L by 3 square by 2. This is moment equation expression. This was originally written without considering the Macaulay's idea. It was giving wrong representation of the load. The correct representation of load is this one. Now, you see the function, singularity function is having 2 square. Okay. So, UDLs should have singularity function 2, concentrated loads should have 1, moment should have 0, power 0. That is the correct representation of singularity functions, and the function should be carried throughout. Okay. This is how the integration technique gives you the deflection and slope in a beam at any location. The other technique what is used is area moment technique. Area moment method is in fact a graphical technique which is used to find slope deflection of a beam at any location. You can find slope and deflection using moment area method at any location, but one value at a time, not like integration technique. at any location you can find the value. You can find the value of deflection only one value at a time. What is this area moment technique? How we apply this to find to this equation? It is by simply rearranging the equation of deflection EI d square y by dx square is mx is the equation of the deflected curve. Just by rearranging we can formulate area moment method. How it is, right? D square y by dx square is mx by EI. Separate the terms there, d by dx of dy by dx m by EI, where dy by dx is slope, is d theta by dx m by EI. So, d theta m by EI dx. This is the first relation what is to be used to find the slope at any point in a beam. Okay. This is in fact does not directly represent the slope. One more thing is, area moment method will not directly give slope and deflection. Okay. You have to use geometry in addition to this method to find slope and deflection values. What it says, this expression says what? If we have a beam, if you plot m by EI values along the length of the beam, we can plot bending moment diagram, divide those bending moment values by flexural rigidity, we will get the curve. Okay. Shape of m by EI diagram may be something like this I take for discussion sake. The beam, corresponding beam, say for example it is bending like this. This is the bent shape of the beam for this particular m by EI values, the m by EI diagram. Select any 2 points on the elastic curve A, B. Draw tangents, tangent at B, tangent at A. The angle between A and B, tangents A and B is d theta, let us say. Draw the ordinates at A and B. The considered portion of the beam is, say for example, negligible length dx, very small length, so that this variation of m by EI values can be neglected, you can take it as a single value. So, this value is m by EI dx. M by EI into dx is representing d theta, change in slope of the two tangents at 2 points on the elastic curve. Okay. So, d theta is equal to m by EI dx. How to apply this result to the beams? Say for example, what we have considered is a very negligible length. If you consider a considerable length in the beam, then you need to integrate this so that any two known points theta A, theta B, we must integrate 0 to x or A to B, what you can represent m by EI dx. So, change in slope between 2 points is nothing but area, total area of integration means summation, total area of such m by ei areas between any 2 points. So, change in slope is nothing but total area of m by ei diagram. This is by just simply rearranging the deflection equation, so that the first theorem which relates slope with m by ei values you can get. We say this is Morse theorem 1 or moment area theorem 1. So, Morse theorem 1 states that the difference in angle between any two tangents drawn at any 2 points on the elastic curve is equal to the total area bound by the ordinates at those 2 points. Okay. Next, further extending this discussion will give you another relation which gives you a helpful theorem to find deflections. That is, taking the same portion again, the negligible length portion dx, if this element, from this element, if you choose any point on this tangent, say for example A, tangent on this point, drop it vertically onto the tangent drawn, say for example some other point C, take, this is tangent drawn at A, I say TA, a point is chosen, point C, I say C dash, it is dropped onto the tangent. We know that this angle is d theta, the point is selected at a distance of x. Okay. So, C dash value is equal to x into d theta, C dash value, where d theta is again m by ei dx. Okay. So, C dash is nothing but, this is the point, this is the tangent, how much it is deviated from the tangent, the point selected, how much it is deviated from the tangent. So, this is termed as tangential deviation of point C from the tangent drawn at A, tangential deviation of C tangent drawn at A. So, TCA is nothing but, what is this, area of m by I diagram multiplied by the distance, area into distance, the first year knowledge, area into distance is nothing but first moment of the area, what we call is first moment of the area. This is applied for a small length of beam. If you apply between any two considerable points, then it becomes tangential deviation any 2 points AB, we need to integrate from A to B m by ei x dx. So, from the first year knowledge, that was what I was telling, integral ai xi is equal to capital A total area into centroidal distance of that area, replacing this with this. Total area, I call it as phi, total area of m by I diagram between A and B multiplied by centroidal distance x bar. Centroidal distance to this area should be measured from A. Why? Because we are calculating tangential deviation of A from the tangent drawn at B. So, wherever you are calculating tangential deviation, that is a point where we want to measure the centroidal distance. Okay. So, this is the second theorem which will help you to relate deflection with this. This will not give you straight away deflection, this will just give you tangential deviation of a point. Okay. How to use these two theorems to solve problems? Just I will give you some example, a simple example. Concentrated load P, a cantilever beam, we apply the two theorems to find slope at A, B, deflection at B. Okay. So, first theorem suggests that difference of angle between any two tangents drawn on any 2 points is nothing but the total area of M by A diagram. So, first we plot M by A diagram for this. Bending moment 0, bending moment P into L, in between it is straight line. By EI, divide all the values by EI, will give you the M by EI diagram. This is M by EI diagram. Choose any 2 points on the elastic curve. Draw the elastic curve, that means bent shape of this beam. I choose 2 points A and B on the elastic curve, this end and other end. Draw 2 tangents. Tangent at A is nothing but the horizontal line. Tangent at B, this is TB. 2 tangents are drawn. So, this is nothing but the line parallel to TA. TA is a horizontal line, it is also a horizontal line. So, this is representing theta B. Okay. So, theta B minus theta A is equal to total area between A and B, area between A and B. Okay. This total area is a triangular area, half BH, half BH. Okay. Theta A is 0, theta B is equal to PL by EI. PL square by 2 EI is the slope value. You have seen that the same value when we wanted to obtain from direct integration, I was formulating some equations, slope equation, deflection equation, evaluating constants, all that. That is a big procedure, whereas it is here much simple. So, graphical representation always will be simple to solve up to some extent. Beyond that, to find the geometric properties may become difficult. Okay. Application of second equation, Morse second equation, is that I want to find this value YB, deflection value. Because of this load, end B has come down to this position. Okay. So, second theorem says that tangential deviation, I want the deflection of B. So, choose point B, draw a tangent at A which will be a horizontal line. Let us find tangential deviation of B from A, tangent drawn at A, tangential deviation of B. So, tangential deviation of B I want from the tangent drawn at A, which is nothing but first moment of the area between A and B from point B. Okay. Tangential deviation of B I want. So, from this you measure the centroid of this total area x bar. X bar should be measured from the point where you are calculating tangential deviation. We are calculating B dash value. B is the point on the elastic curve, B dash is the projected point onto the tangent, B dash is the deviation, tangential deviation. So, total area half BH, centroidal distance 2/3 of L. It is a triangle, from this end it is 1/3, from that end it is 2/3 of base. So, it is nothing but PL cube by 3 EI, 2 and 2 gets cancelled. TBA, tangential deviation of B from the tangent drawn at A, is nothing but B dash, which is nothing but YB, deflection YB. So, deflection can be calculated straight away, okay, by choosing the tangent at A. Hence, this become simple case. So, this is what the application of moment area theorem. For a simple case I have discussed, we can extend this to any type of problem, where the difficulty come is when you have UDL, the bending moment diagram will be a second degree curve. When you have a triangular load, the bending moment diagram will be third degree curve. So, to estimate geometrical properties like area, centroid will be difficult. Hence, this moment area technique is best applicable up to concentrated loads. Furthermore, if at all, if you want to apply, it will be up to UDLs. Beyond that, this method is not suggested. Okay. Still, you can solve if you can estimate geometrical properties correctly. Okay. So, the third method what is to be discussed is conjugate beam method, a special case of moment area theorem. The time will not permit, we will discuss in the further more lectures. Thank you very much.